Hello, welcome to our channel Search Solutions for You. I am Sushmita Kiran. Today we are going to discuss the topic reduced phase rule and its application to two component system. So let's start. Reduced phase rule. We know the normal phase rule equation is f dash is equal to c minus p plus 2. Okay, so this is our regular normal phase rule equation. When we come to two component system, in our two component system, we know components will be 2, and so f will be 2 minus p plus 2, or you can write 4 minus p. I am only substituting the value of c as 2 because it is a two component system, so number of components will be 2. So we will have the modified equation as 4 minus p. Now phase can be either 1 or 2 or 3. So these are the three possible values allowed for phase. Now suppose when p is equal to 1, we will get f is equal to 4 minus 1, that is 3. And when p is equal to 2, you will get f is equal to 4 minus 2, and that is 2. And when p is equal to 3, we will get f is equal to 4 minus 3, that is 1. So when the value of p is 1, you will get the value of f as 3. Okay. So what is f? F is the number of degrees of freedom, that is the number of independent variables that is required for defining a system. So when f is 3, you need to have temperature, pressure and composition for describing a system. So you can't represent your phase diagram on a paper. Okay, why? Because 3 variables are there, so it will be a 3-dimensional diagram, and 3-dimensional diagram, so we can't represent on a board or a paper. So for that, like for our convenience, what we are going to do, we are going to modify our phase rule equation. Okay, so for a two component system, we know that number of components is 2. The value of p can be 1, 2 or 3. So when p is equal to 1, at that time you will get the value of number of variables f as 3, which is not possible because we can't represent it on a paper. So for our convenience, we are going to modify our phase rule equation, and then we will get reduced phase rule equation. So what is our reduced phase rule equation? Reduced phase rule equation is f dash is equal to c minus p plus 1. F dash is equal to c minus p plus 1. This is our reduced phase rule equation. Instead of this 2, you will have 1 in your reduced phase rule equation. Okay. Now this reduced phase rule equations you will be using only for condensed systems, that is for the systems in which pressure effect is very less. So your two variables will be temperature and composition. Okay. So that is our reduced phase rule. So reduced phase rule we are applying only for two component system, that is f dash is equal to c minus p plus 1, and this is our reduced phase rule equation. A simple eutetic system. In two component system, we have to learn the phase diagram for a simple eutetic system. What is a simple eutetic system? A eutetic system means a system which consists of two components. A system having two components that are completely miscible with each other, completely miscible in liquid state, and do not react with each other. Do not react chemically. So this is a eutetic system. A eutetic system is a system which consists of two components that is completely miscible in its liquid state. In its liquid state, it will be completely miscible and they do not react with each other chemically. That is a simple eutetic system. An example for simple eutetic system is lead-silver system. Lead-silver system, PBAG system. These two solutions will be completely miscible with each other and they do not react with each other, but in solid state they will exist as separate two solids. So that is a simple eutetic system. Now let us discuss the phase diagram for a simple eutetic system. In this phase diagram, we are plotting our diagram with temperature versus composition. For one component system, we plotted temperature versus pressure. And those who didn't watch my previous video about one component system, I will provide the link in the description box. Please do watch it. Now, here we are plotting our phase diagram with temperature against composition. We are neglecting pressure because we are studying about condensed systems. Condensed systems, pressure effect will be less. Now, this point A represents the freezing temperature of component A. In our system, we have two components A and B. Now, this point or this temperature A represents the freezing temperature of A. At this particular point in our system, only A is there, no B component is there. Now, when we start to add small quantities of B into our system, what will happen? Its freezing temperature decreases and finally it will reach at a point C. Okay. Initially in our system was having 100% of A, no B was there in our system, and A was having a freezing temperature at the point A. When we started to add more small quantities of B into our system, what will happen? Its temperature decreases and attains a temperature C. C is the minimum temperature that is attained when we are adding small quantities of B into a system that contains only A. Okay. So, its temperature decreases. Now, in this area, we will have solid A and a solution of B in A. Okay. We will have a solid A and solution of B in A because we were adding small quantities of B into our system. Now, that is over. Here, initially we had 100% of B and 0% of A. So, B is the freezing temperature of pure component B. In our system only B is there, no A is there. Now, when we started to add small quantities of A into our system, what will happen? Its temperature decreases and attains at a minimum temperature or minimum temperature of C. Okay. So, initially it was B. When we started to add small quantities of A into our system, the temperature decreases and finally it arrives at a point C. Below C, the temperature won't decrease if we add further A or B into the system. Okay. So, C is the minimum temperature that is attained by both A and B when we add B into the system of A and A into the system of B. So, this curve AC represents the freezing curve of A and BC represents the freezing curve of B. Okay. Now, outside the curve AC and BC, we will have a liquid melt region. This is an unsaturated region where we will have the mixtures of solution of A and solution of B at any composition. Okay. So, this is the liquid melt region. This is the freezing curve of A and this is the freezing curve of B. This region will have solid A and solution of B in A because we initially had A in that. So, we are adding B to A. Now, this phase will have solid B plus solution of A in B. Okay. Initially we were having B in the system. So, we are adding A to the system. So, we will have a solution of A in B. Don't get confused. This is solution of A in B and here we will have a solution of B in A. Okay. Now, this is liquid melt region, that is fine. Now, below this, if you see, you will have a small area where you will have solid A and solid B. So, C is the minimum temperature, below which if we are further decreasing the temperature, what will happen? Both A and B will get solidified. We will get solid A and solid B. So, in this area, we will have solid A and solid B. Outside region, you will have liquid melt region that is having solution of both A and B at any composition. And in this region you will have solid A plus solution of B in A and this portion you will have solid B plus solution of A in B. So, this is our phase diagram for a simple eutetic system. Initially you are having 100% of A and as we move to this side you will have 0% A and 100% B. Fine. Now, let us discuss about each areas separately and we will apply our reduced phase rule equation to find out the value of F dash. That is only we have to do in simple Eutetic system phase diagram. First, let us consider the curve AC, that is our freezing curve of A. Now, inside that region, since this is a two component system, we know number of components will be 2. Okay. Now, how many number of phases are there? Number of phases P. We have solid A, so we have a solid phase and a solution phase. So, solid A is there, so that is phase number 1. And a solution of B in A. So, one solution is also there. So, that is 2. So, we will have number of phases 2. Now, calculate F dash. F dash is equal to C minus P plus 1, that is 2 minus 2 plus 1, or you can say F dash is equal to 1. Our system is univariate, or we can say it is monovariate in the curve AC. Now, consider the curve BC. For the curve BC, we know that there is also 2 phases are there. Number of components will be 2 and number of phases will be again 2. Why? We will have solid B, that is one phase, and solution of A in B. We have a solution also. So, that is one phase. So, totally we will have 2 phases. And here also when you will apply reduced phase rule equation, you will get the value as 2 minus 2 plus 1, that is 1. So, your system is monovariant or univariant with respect to the curves AC and BC. Now, let us consider the point C, okay, the point C. So, what is the peculiarity of point C? Point C is the minimum temperature that is attained by both A and B. We know that this is the temperature at which both our A curve and B curve is meeting. So, at that particular point, solid A, solid B and the solution of A and B exist in equilibrium. Okay. At this point, solid A, solid B and their solutions, both all are at equilibrium with each other. So, number of components F dash is equal to C minus P plus 1. The number of components is 2 because this is a 2 component system. Now, what is the number of phases? How many number of phases are there? Solid A is there, solid B is there, and we will have a solution of A in B. So, total number of phases is 3. Solid A will exist as separate phase, solid B will exist as a separate phase, and the solution of A and B will exist as a separate phase. So, we will have totally 3 phases. Now, apply F dash will be equal to 2 minus 3 plus 1 and our value will be 0. So, we can say that at the temperature C or at the point C, our system is invariant because F dash is equal to 0. Now, this point C is called eutetic point. Eutetic point. So, the point C is called eutetic point, that is the minimum point, minimum temperature to which both our A curve and B curve can attain, or we can say that the point at which solid A, solid B and their solutions coexist in equilibrium, and that point is called eutetic point. And the temperature corresponding to eutetic point is called eutetic temperature, and the composition corresponding to eutetic point is called a eutetic composition. So, if you extend your curve, this particular composition and this particular temperature, this is a eutetic temperature and this is your eutetic composition. Okay. So, that is all about point C. Now let us consider the area ACB, this outside region, that is ACB. So, area ACB. Okay. Now, in that region, The number of components will be 2, and what is the number of phases? It exists as a liquid melt region which will have the solutions of both A and B. Since the solution of A and B are completely miscible with each other, there is only one phase. So number of phases will be 1. Okay. Don't get confused with the number of phases. If you have 5 solids, then your number of phases will be 5. If you have 10 solids, then your number of phases will be 10. But if you have 2 solutions that is completely miscible with each other, then your number of phases will be 1. Okay. So number of physically or separable boundaries should be there, then only you can call it as a phase. Fine. So since A and B are completely miscible with each other in solution, so when you mix A and B, they will be completely miscible and they exist as a single solution. So your liquid melt region number of phases will be 1. So number of phases 1. Therefore F dash is equal to C minus P plus 1 is equal to 2. So your system is bivariant in this region, that is A, C, B. I have labeled in our diagram D and E for this line. If you consider the area below the line DE, below the line DE you know that solid A and solid B exist. So number of components is 2 and number of phases will be 2. Why? Because you will have solid A also, solid B also. Solid A and solid B represent 2 phases. So number of phases will be 2. So F dash will be C minus P plus 1, that is 1. So your system is univariant in this area. Okay. So that's all about our 2 component system. In the 2 component system, we have to apply our reduced phase rule equation. We will be applying our reduced phase rule equation to all the areas, to the curve AC, to the curve BC and the liquid melt region and the solid A and B region. So we have to apply our reduced phase rule equation to all the areas present in our phase diagram, and you need to calculate the F dash value. Let us summarize our phase rule diagram for simple eutetic system. In our simple eutetic system phase diagram, for the areas ACD and BCE, ACD this portion and BCE this portion. For these 2 portions, C is equal to 2 since number of components is 2 for a 2 component system. Number of phases will be 2 because we will have a solid phase and a solution phase. So F dash will be equal to 1. Our system will be monovariant. Okay. Now for the area ACB, that is this liquid melt region ACB. For our liquid melt region, we have only solution phase available there. So number of components is again 2. Number of phases is 1. So F dash will be 2. Our system is bivariant system. Now for the area under DE, that is this portion, you will have solid A and solid B. So number of phases is again 2. So your F dash value will be 1. That is, this is a monovariant system. Now for the eutetic point C, when you consider the eutetic point C, you will have solid A, solid B and solution of A and B are in equilibrium with each other. So number of phases will be 3 and number of components is again 2. So your F dash value will be 0. Eutetic point C is the point at which solid A, solid B and the solution of A and B coexist in equilibrium. So number of phases will be 3 and number of components will be 2. So F dash will be 0, that is your system is invariant. Okay. So system is invariant at point C and the system is monovariant for this portion, this area and for our area under D, this area. So for all these 3 areas, your system will be univariant or monovariant. Only for this liquid melt region, your system will be bivariant. So this is our phase rule diagram for 2 component system. Okay. Now I told you an example for 2 component system is PBAG. That is lead silver system. Okay. For lead silver system, always in this 2 component system, one component will have lower freezing point than the other. So your one curve should lie below and the other curve should lie above. Okay. So suppose in your examination, if it is asked to draw the phase diagram for lead silver system, then you have to consider lead as your component A and silver as your component B and draw the same diagram as we have learned now. Okay. For any eutetic system, if they have given any examples, you can write A as component 1 and B as component 2 and just change the name as per the given example. Okay. So that only we have to do. So this is simple eutetic system phase diagram. Thank you for watching my video. If you like my video, please don't forget to like, share and subscribe my channel. If you have any suggestions, please feel free to comment in my inbox. I'll come up with a new video next time. Until then, bye bye.